Hello everyone. It's my honor to introduce our work, Precise Integral in NeRFs, Overcoming the Approximation Errors of Numerical Quadrature. All the authors are from the Institute of Computing Technology, Chinese Academy of Sciences. Neural radiance fields, also called NeRF, is a representative method for representing complex scenes using neural networks. Given input images, NeRF optimizes a volumetric scene representation that takes a 5D coordinate as input and maps this coordinate to the corresponding volume density and view-dependent color. Using volume rendering, NeRF combines these values along the camera array to compute the color of each pixel, generating the final image. This differentiable process allows NeRF to be optimized with rendering loss across camera views from input images. Before delving into our work, we first revisit the volume rendering process and examine how existing NeRF methods approximate the integral through numerical quadrature. In the volume rendering integral, the color of a ray R, spanning from point T0 to Tn, is determined by the points distributed along the ray. Each point is characterized by its density sigma and view-dependent color C. The integral interval between T0 and Tn can be discretized into n segments, transforming the rendering integral into a summation form. In this summation form, T denotes the transmittance of a segment, and C represents the accumulated radiance of a segment. In existing NeRF methods, the density and color properties of a 3D point are predicted by a neural network. As a result, the transmittance and accumulated radiance are derived as integrals of a complex neural network function. To simplify this integration, NeRF assumes that both the color and density remain constant within each segment. This assumption enables a closed-form approximation of the transmittance and accumulated radiance. While this approximation offers a differentiable alternative to the exact integral, it inevitably sacrifices some accuracy. It is worth noting that various methods can be used to approximate the function within a segment to achieve a differentiable integral approximation. NeRF employs rectangular approximation, while other approaches include trapezoidal approximation and parabolic approximation. However, none of these methods can precisely capture the behavior of the original function. So, what's the problem with using quadrature as an approximation? Let's take the approximation of the transmittance term as an example. During training, the model estimates the transmittance of a segment based only on the density value at the starting point of that segment. Consequently, the gradient of the loss function with respect to the transmittance is directly backpropagated to the density prediction at that starting point of a segment. However, during training, multiple segments that share the same starting point may be sampled. For instance, segments x0, x1 and x0, x2 both have x0 as their starting point. This results in the density prediction at x0 receiving gradient signals from multiple segments, which introduces training ambiguity and complicates the optimization process. Next, we present two intuitive examples to illustrate why supervision signals from different segments can be inconsistent. In the first example, within the same training batch, two segments, x0, x1 and x0, x2, originating from the same starting point, but along different directions, are sampled. The dashed ellipse in the illustration represents an object in the scene. The density inside the object is greater than 0, while the density outside the object equals 0. The transmittance of segment x0, x1 is 1, driving the gradient to reduce the density at x0 to 0. However, the transmittance of segment x0, x2 is less than 1, thus pushing the gradient to increase the density prediction at x0. In the second example, two segments with the same starting point, but different lengths are sampled across different batches along the same direction. Similar to the first example, segment x0, x1 tends to push the density at x0 towards 0, while segment x0, x2 encourages a prediction greater than 0. This results in ambiguous supervision. A direct consequence of such ambiguous supervision is that points near the object surface tend to have density predictions higher than their true values, leading to the phenomenon of density spread. we have indeed observed the phenomenon of density spread in existing NeRF methods. The images in the leftmost column represent the actual NeRF training data set. The images in the middle column are rendered using models trained with existing methods, for example, NeRF, instant NGP. Can be seen that the surface of the object exhibits a spread of density, as highlighted by the red box in the figure. This observation aligns with our theoretical derivation, providing evidence that the quadrature approximation leads to ambiguous density prediction. The images in the rightmost column are rendered using models trained with our method. Can be observed that the phenomenon of density spread is significantly reduced, leading to more accurate geometry and color reconstruction of the scene. So, let's introduce how we eliminate the training ambiguity caused by the quadrature approximation. We perform a Taylor expansion of the transimitance term at t and retain the Lagrange remainder. Compared to NeRF's quadrature computation, it can be observed that they directly discard the Lagrange remainder term, which contributes to training ambiguity. In contrast, we observe that the entire Lagrange term is a bivariate function of the segment's endpoints. Building on this insight, we propose a novel segment encoding method that incorporates information from both endpoints of the integral segment. This approach implicitly accounts for the Lagrange parameter, effectively eliminating the ambiguity. This is the overview of our PrecNeRF pipeline. For a segment to be a long array, we compute its representation by concatenating the encodings of its two endpoints, using either sinusoidal encoding as in NeRF or hash encoding as in NGP. This combined representation is then passed through an MLP network to obtain the integrated information of density and radiance for that segment, effectively learning a segment density field and a segment radiance field. Furthermore, the segment density and radiance are incorporated into the volume rendering process. We compare our methods with their counterparts that use numerical quadrature. Refining the quadrature into a precise way results in a 1 decibel average increase in PSNR for synthetic scenes and 0.4 decibels for real-world scenes. PrecNeRF also outperforms grid-based and deterministic integration methods by a notable margin, achieving state-of-the-art rendering results. Additionally, PrecNeRF improves rendering accuracy of PNeRF across all resolutions in the multi-scale synthetic NeRF dataset, demonstrating its generalization to various NeRF architectures. Here are some visual comparisons of the rendering results. In the barn example, the improved method demonstrates more accurate reconstruction of scene geometry, such as the decorations on the roof edge and the red metal pipe. In the materials example, the improved method provides finer rendering of the texture details on the reflective spherical surface. Similar examples can be observed, such as the geometric details on the wine holder and the rendering of the transparent glass dome on the spaceship. To make comparisons more intuitive, we reduce the number of sampling intervals when training NGP and PrecNGP on the synthetic NeRF dataset. The number of sampling points decreases from left to right, whereas the length of the integral interval, as well as the approximation ambiguity, increases. Compared to baseline method, our improved one effectively handles ambiguity, preserving both thin geometries and complex textures. We also conducted several ablation studies, which show that our integral computation method outperforms traditional approximation techniques. In addition to improving rendering quality, the use of segment representation also enhances the accuracy of depth estimation. Further experimental results can be found in our supplementary material. In conclusion, our contributions are threefold. First, we utilize Taylor expansion to show that existing NeRF's quadrature neglects the remainder term, causing training ambiguity. Second, we propose segment representation, enabling the neural network to model the remainder term for precise rendering. Third, our method can be seamlessly integrated into existing NeRFs and achieve state-of-the-art performance on multiple datasets. Thank you for your attention.